This is how you measure DNA. I created this formula. It's pretty simple. All you really have to do is measure your masses and tag you need all your masses of your nucleotides, total mass of your DNA. You're basically going to chop all your DNA up into nucleotides with enzymes or acids or bases or whatever. You need total masses of your nucleotides, which is so many base pairs per enzyme, restriction enzyme or whatever they're called. Then you have to use PCR to copy the nucleotides, and then you tag the ends of the nucleotides, the beginning and the end, and it identifies the first base pair with the last base pair. And you need to know, really, truly, you need to know that the double helix is the whole point to DNA, and you have to have all of the segments, the total segments, from the beginning to the end of someone's DNA. And you may have to copy these DNAs or grow them in a laboratory and chop them up and everything else, and use PCR. And then basically you just follow this formula right here, and you add up all the masses of the base pairs that follow the double helix shape, which are all masses of the nucleotides, and you add the nucleotides together, and you get the total DNA by the mass links of the double helix order of one entire DNA. And also, when it comes to math is nothing but various amounts of kinds of ratio calculations. Here's another one that I want to say. All atoms of type have an identity, and it's their mass among electron configuration, and energy inputs and outputs. They have different ways of measuring atomic identities, all atomic, molecular, and compounds. But the limits of physics will only allow such a large compound to be measured by mass spectrometry. So you use algebra to figure out the arrangements of organelles and cell parts and stuff like that, to learn the biochemistry of parts of cells. And then basically you compare that with an algorithm, and you have to know the shape of your organelles, so you may need an electron microscope to get the shape or a generic shape. And then basically you use algebra and computers, kind of like DNA, like we did the DNA down here. You compare it to a shape, and you algebraically fill in from an order. You may have to also tag your parts or identify its mass, and then you have to have the total mass of the organelle or whatever. You have to have an identity. Your key ingredient is several identities of masses or any kind of identity that you can gather. And tagging and measuring energy that identifies something is pretty key to this. And then basically you simulate it with a computer, and then when you want to react medicine in that world of energy, basically that's what it is like showing the reactions of of chemistry in biology, and there's a lot of identities and variables, and there are a lot of elements, and there are a lot of energy states and motions and potential events, basically. But you want to, you got to get the masses, the volumes, the shapes, the electron configurations, the energies, the radiations, the colors, the force, the flow, the gravities. There's all kinds of things that you want to measure about molecules and compounds in bioresimulation measurements. But here was my last grocery list. It's pretty cool. This is what I bought. I had to put back the Lucky Charms and some other stuff, but I got some good food. Eating a lot more vegetables these days instead of bread and meat. But what you want to do is show the physical chemical simulation. That's the key ingredient, and those are all like these formulas at the bottom here. Basically, just like doing DNA here, you're going to follow a path of identities. Key to science is identifying the objects and their events. So that's pretty much it for this video. But this is exactly how you identify the algorithm in a computer sequence of the measurement of DNA after you use the DNA throughput to measure the tagged nucleotides, and then you calculate the base order of each nucleotide, and then you sum the nucleotides up to equal the entire DNA. It follows the shape of a helix. So, like, if you were doing that to an organelle, it's basically the same principle, I would say. You have to find a way to identify your masses and then your shapes, and you have to put it together just like putting together a puzzle, except you're using mathematical algorithms, and you have to measure identities. That's the key ingredient. So that's how biochemistry does its job, and that's pretty much how they assume medicine, if they do ever assume medicine. However, I'd say that there may be subject for error if everything doesn't go perfect. There may be lost information somewhere, but especially in the usage of medicine and its actuality, they assume that they know more than they really know, and that they know that the body does or doesn't react or change or have some kind of event that they think happens, but there could be a lot more to it. So there's more variables than they imagine. and there could be differences that they don't know about. So medicine might not be as accurate, not to mention there's a law of chemistry that chemicals react variably. They try to say that there are receptors and transmissions and emissions and things like that, and that these receptors are specific, like enzymes are specific and stuff like that. But I don't think receptors themselves, especially in the brain or wherever they might be, are always exactly specific. They can actually intercept various possible molecules or compounds, depending on how large they are and if they're positively charged. We know that a positive charge is a positive charge, which means that it can bind to anything. Positive charges don't discriminate on what they bind to. They'll bind to anything. If you take two chemicals, one's positive and one's negative, basically they will bind, or they will break apart and reformulate, and they will cause other combinations to happen. So positive and negative bind in almost all cases, in any case. So you really can't say that structures discriminate when they don't. That's the law of chemistry. Positive, negative equals bondage. Or it also potentially equals breakage. So that's it. This video, I think I'm going to call it measuring biochemical identities. Thanks for watching.